Welcome to another installment of the Robinson Twins present Earth is Our Spherical Home Planet. In this installment, we'll be looking at one of the ways you can prove experimentally that the Earth is a rotating sphere. And that was done by Léon Foucault in Paris, France, in 1851. And it's been repeated many times since. In fact, there's more than 200 Foucault pendulums around the world at various museums and educational institutions. And even in public places like the United Nations has one. So we'll look at how that pendulum works and what can be derived from that kind of experiment and what it proves. So let's take a look. Scientists have known for centuries that the Earth is a rotating sphere, but the rotation was only estimated from indirect measurements such as sunrises, sunsets, moonrises, moonsets, and stars rotating in opposite directions in the northern hemisphere versus the southern hemisphere. It wasn't until 1851 when French physicist Léon Foucault came up with a way to measure that rotation directly. He first demonstrated the pendulum publicly in 1851 February in the meridian of the Paris Observatory. A few weeks later, he made his most famous pendulum where he suspended a 28-kilogram brass-coated lead bob with a 67-meter-long wire from the dome at the Pantheon in Paris. In researching the Foucault pendulum, I found an interesting side note, and that is the effect of precession had been discovered 190 years earlier, but the researcher, the scientist, didn't realize what the cause was. His name was Vincenzo Viviani. He was a student of Galileo, and he was studying the pendulum. And he considered the precession a nuisance, so instead of realizing what it was and noting it, he suspended his bob from 2 ropes instead of 1 to eliminate the effect. If he had realized what it was, we might be calling this the Viviani pendulum instead of the Foucault pendulum. We went to the California Academy of Sciences in San Francisco and recorded their Foucault pendulum. Once the pendulum starts swinging, it maintains its plane of oscillation, and it's the Earth moving under it that causes it to appear to go around in a circle. That process is called precession, and you can calculate exactly how long that should take. At the North and South Pole, it should take 24 hours, just like the Earth's rotation, but as you get closer to the equator, it will take longer and longer, until at the equator, it won't precess at all.
Once this starts going in a certain direction, it maintains that direction. So the fact that it's knocking down pegs around this circle is because the Earth is rotating beneath it. The Earth is rotating, and that causes the floor beneath it to rotate also. So this thing will actually knock over pegs throughout a 24-hour day. It will go through one rotation, one circle. Yes, it will.
Looks like it's right on top of our model where you have people in the lab and people in the field.
Knock it down.
Yeah, knock it down, knock it down.
So close. Didn't get this one though. There it goes. Observing the northern hemisphere from the North Pole, we'd observe a counterclockwise rotation. So the pendulum goes clockwise, which is what we observed. The pendulum at the California Academy of Sciences uses pegs placed in a circle around it for the pendulum to show its progress by knocking the pegs over. Other pendulums around the world use a smooth sand at the bottom so that the pendulum actually traces a pattern in the sand itself, so you could look back over time and see its progress. And if you could see the Earth's rotation from above the South Pole looking down on the Earth, you'd see that the southern hemisphere is rotating clockwise, so the Foucault pendulum in the southern hemisphere would turn counterclockwise. And later on you'll see an experiment where that's exactly what's observed. But part of the problem with the pendulum originally was that it could only swing for so long, a few hours, but that was enough to demonstrate the principle and that it really does work. Museums now have a way of keeping that swing going for days, weeks, and even months at a time, and we'll look at that in a little bit. But first, let's look at some of the math behind it, just briefly, the math behind the Foucault pendulum. The change in the angle, apparent angle of the pendulum is called precession. So the precession period time to complete one full rotation of the swing plane around the circle is T sub P equals 24 hours divided by the sine of the latitude, the angle. So the North Pole at 90 degrees north comes out to a sine of 90 degrees is 1, so 24 divided by 1 is 24 hours. And that's what it should also take at the South Pole, 90 degrees south. For Paris, which is where Foucault first demonstrated this, the latitude was 49 degrees north, so the time took, as you look in the math, 31 hours and 47 minutes. And then San Francisco, where we observed the Foucault pendulum at the California Academy of Sciences, is at 37.7 degrees north. And according to the math, that would come out to 39 hours and 52 minutes. Of course, at the equator, 0 degrees, the sine would be 0, and you'd have no time. The equator, the pendulum does not precess at all. An interesting fact about this formula is that if you had a Foucault pendulum and measured its time to complete a 360-degree precession, you can work backwards and find out what your latitude is without using a sextant. Pretty nifty. Now, comparing our calculation to what the California Academy of Sciences says on their sign, here you can see it tells us how long it takes for each peg to fall, which is 35 to 40 minutes, and it will take about 39 hours, according to the sign. So our calculations were correct. So scientists have figured out a way to make the pendulum continue swinging instead of having to restart it manually every few hours. And that method that they've come up with does not change the direction of the pendulum. So let's look at the Houston Museum of Natural Science explain it.
Every pendulum on Earth needs a little nudge to counteract mechanical friction and air resistance. This nudge, for our pendulum at least, is actually a slight electromagnetic tug on a metal collar at the top of the 61-foot, 7-inch cable itself. The electromagnet is actually a circular ring, triggered at the ends of the 7-ish second total swing, or period, technically. Since it's a ring magnet, it only tugs in the same direction the cable arrives. It does not alter the direction or inertia at all. This mechanism simply maintains the momentum of the 180-pound mass against friction and wind resistance. It's very slight, but it's there. And well, in our case, this mechanism has stopped. Because like all mechanical things, it needs maintenance from time to time, especially after literal decades of virtually non-stop operation.
A few months later, they had a follow-up video explaining how they got it going again. So here's that.
We were doing some repairs or maintenance on other parts of the building, which means we had to shut off power to this part of the building and thus shut off power to the mechanism that keeps the pendulum swinging. So when they flipped the power back on, all the busyness of the holidays happened and our maintenance crews weren't able to get back up there until January. Now, when our maintenance crew went up there and found everything to be in working order, nothing appeared to be fried, there's no magic smoke coming out of it, they realized what they actually had to do was reset all the parameters, readjust these dials. So the way it works is you have dials for things like the strength of the electromagnetic pull on the collar, or amplitude, whatever you want to call it. You also had a dial for the duration of that very minute tug. So they had to finally tune all of those dials to get it locked in to this nice oscillating frequency that allows the pendulum to remain swinging 24/7, 365, or until the next time electrical gremlins decide to strike. So our maintenance team is awesome. We are very happy to know that there actually wasn't anything wrong with the pendulum, which is great because these things are built one-off by hand. And the person who built this one-off Foucault pendulum for us built it back in the 1960s and 70s. That's when it was installed. So it's been quite a few decades since this thing was first set into motion. Traditionally, Foucault pendulums were started by a string. It was pulled back and attached to a string, and then you lit a candle and put a candle under the string, and the string would snap, setting the pendulum in motion for a few hours. Some people ask, well, if you turned off the electromagnet on top, how long would it swing? The answer is it would swing for a few hours. And that few hours was long enough to demonstrate that the Earth was in fact rotating underneath the pendulum. It's not the pendulum going around the outside, it's the Earth rotating under the pendulum.
We'll provide a link in the description to both of the videos that the Houston Museum of Natural Science did about their Foucault pendulum. And I would also like to remind people that both the California Academy of Sciences and the Houston Museum of Natural Science have YouTube channels, so you should check those out. Now for our final look at the Foucault pendulum in this video, we're going to look at an experiment that was done in 2001 by 3 scientists at the South Pole. So let's check that out. The Foucault pendulum experiment was done at the South Pole Station in 2001. It says winter, but it was actually the summer for the South Pole. They determined the period to be 24 hours plus or minus 50 minutes. The acceleration due to gravity was determined to be 9.85 meters per second squared plus or minus 0.03 meters per second. The rotation of the Earth was in a clockwise direction of looking down from above the South Pole, so the Foucault pendulum turned counterclockwise. The scientists conducted their experiment in a newly constructed stairwell 6 stories high that had not been put to use yet. They had very challenging conditions, at negative 90 degrees Fahrenheit, an altitude of 11,000 feet, atmospheric pressure only 660 millibars where sea level is 1,013 millibars. But the thinner air did allow for the pendulum to swing longer due to less air resistance. In the final line of their report, they state, "We have demonstrated a physical phenomenon confirming that we are on the axis of rotation of the Earth. Although the result matches our hypothesis and nothing new has been discovered, we have placed ourselves among the stars and standing beside Galileo in recognition of our planet as a rotating sphere floating in the heavens. We have thus enhanced our own understanding of our place in the universe. The South Pole Foucault pendulum is still in place, and periodically one of us will go out and start it swinging and take further data to refine our findings." At this point, you might be wondering why the precession would take longer as you move away from the pole. So let's go over that real quick. There are 2 factors affecting the rotation of the pendulum, and that's the rotation of the Earth, but there's also another factor I've seen called traveling. Now, at the North Pole and the South Pole, it's all rotation and no traveling, so you get 24-hour rotation of the Foucault pendulum around the circle. But as you get farther from the North Pole or the South Pole, you're getting farther from the axis of rotation, and that factor is referred to as traveling. So at the equator, it's all traveling and no rotation. You're farthest from the axis of rotation. And at the North and South Pole, you're right on the axis of rotation and there's no traveling. So the farther you get from the North Pole or the South Pole, the longer it takes for the precession to finish. And they also go in opposite directions. Further proof that we live on a spherical Earth that's rotating. Thanks for watching. Now be sure to like and subscribe.